Okay, I think that looks like folk are back in, so let's make a start on work sharing directives. So we've mentioned this already, but just to recap, work sharing directives are directives which appear inside a parallel region, and they indicate how work should be shared out between threads. So the default for a parallel region is that all the threads execute the block of code. So all the threads execute all the code inside a parallel region. So clearly we can do what you've already been doing in that first exercise with the Mandelbrot set, is to manually use the thread ID and the number of threads inside a parallel region to divide up work. However, that's not particularly nice, and it's a little bit inconvenient. So OpenMP provides these extra facilities for some of the common cases where you want to divide up work between threads. So, and the ones I'm going to talk about here are parallel, do, or for loops. So how to parallelize loops, and then also the single and master directive. So as I said before, loops are the most common source of parallelism in most codes. So parallel loop directives are very important and probably what you will use OpenMP mostly for, at least to begin with. So a parallel do or for loop does what you expect. It divides up the iterations of the loop between the threads. Okay? So this directive appears inside a parallel region, indicates that the work should be shared out between threads instead of replicated. If we just have a plain old loop inside a parallel region, then all the threads will execute all the iterations of the loop. So instead, we want them to be shared out. There is also a synchronization point. So it's actually one of these barrier synchronizations at the end of the loop. So all threads must finish their iterations before any thread can proceed and execute any other code inside the parallel region. That's the default behavior. There is a way to get rid of that implicit barrier, which we'll talk about later on in the course. There isn't a corresponding synchronization point at the start of the loop. So as soon as any thread reaches the parallel loop, it can go ahead and start executing its iterations, regardless of whether the other threads have also reached the start of the parallel loop. Okay, so the syntax looks like this. For Fortran, it's $OMP do, followed immediately by the do loop. And then the end do directive is actually optional. The compiler is perfectly capable of working out where the loop ends, but it's just tidy or convenient, if you like, to use the end do directive, so that it's like all the other OpenMP constructs or most of the other OpenMP constructs in Fortran, where you have a starting directive and a matching end one. But you don't need to use it. If you don't like it, you can leave it out. For C and C++, it's #pragma OMP4, followed immediately by the for loop. So the thing to be aware of here is that the for loop itself cannot be enclosed in a pair of curly braces. So the very next thing that appears after the OpenMP4 directive must be the C for loop. Okay? So no intervening. You can't put an extra set of curly braces round the outside of the for loop. Again, as I hinted before, there are some restrictions for C or C++ loops because actually the C4 construct is really a general while loop with some extra syntax in there. You can do pretty much anything you like in there and break out, have any condition and break out any condition to end it and break out where you like and so on. Okay. So there are some restrictions on the form it can take if we want to apply an OpenMP4 directive to it. So basically, it has to have a determinable trip count. Okay, so the number of iterations must be computable before the loop starts executing. So that means it has to have this sort of canonical form. So it must look like for some variable equals some initial expression, and then the condition must be var less than or equal, or greater than or equal to some other value, and then the increment expression must be var equals var plus or minus something, or the usual semantic equivalent such as var plus plus or var minus minus or plus plus var or whatever you like. Okay. And the other restriction is that you cannot modify the loop iterator variables. You can't modify var inside the loop body. Which is perfectly legal C. So here would be an absolute classic example of a typical thing you would want to do with a parallel loop. And so have this loop which has independent iterations. So all the calculations of the element of the array B on the left-hand side are independent of each other, so they can be done in any order. We need to be inside a parallel region in order to have multiple threads to execute. And then we apply the do, or get my pointer here, we apply the do or the for directive in front of the loop, which shares out the iterations of that loop between the threads instead of duplicating the entire loop on every thread. Okay. Actually, this pattern is so common that OpenMP gives you a shorthand form which combines both the parallel region and the do or for directives. So you can, instead of having a separate parallel region and then enclosing a do directive, you can do it all on one line with OMP parallel do in Fortran, followed immediately by the do loop, optional end parallel do. Or in C, you can do hash pragma OMP parallel for, immediately followed by the for loop. So this is what the compact or combined directive form looks like in Fortran and in C. So in terms of what clauses are available, the do or for directive, you can have private, first private, and reduction clauses which refer just to the scope of the loop. Okay, so you can have, it's possible you can have variables which are shared on the parallel region, and then you can have private or first private or reduction behavior just for the scope of the loop. Okay. Private and first private are fairly unusual. However, the ability to do reductions and have the reduction computed at the end of the loop rather than at the end of the parallel region is a reasonably common use case. It's not unusual to find code where you have a parallel region that has, say, more than one parallel loop in it, and you want the result of the reduction, you want to use the result of a reduction on a loop in subsequent code inside the parallel region. So in which case you need to have the reduction clause on the loop, on the do or for directive, rather than on the parallel region. When you have it on the parallel region, then the reduction doesn't happen until the end of the parallel region, which is going to be too late. Okay. The parallel loop index is private by default, so you don't have to declare it as such, though you won't get any complaints if you do. Okay, it's fine if you want to, but you don't need to declare the index of the parallel loop as private. And as I mentioned before, other loop indices, so if it's other loops which are not the parallel loop, they are private by default in Fortran, but not in C. Okay, so that's a possible trap you can fall into. Though if you declare all your loop indices in place, then that's which most people do in C programming these days, then that's not going to be a problem. Okay, otherwise, the combined directive can take everything that you can put on a parallel directive. But if you're new to OpenMP, then just be careful. It's easy to get confused because the combined directive has different semantics from the loop directive and has different semantics from the parallel directive. So you just need to be clear about which you are using where. Okay, so for example, you will get, if you have a parallel region and then you put a parallel do inside it instead of a do, then you will not get the behavior that you wanted. It's legitimate. It's legitimate OpenMP. You're creating nested parallel regions, which we'll talk about tomorrow, but that's probably not what you wanted, and you may end up with broken code if you do that. Okay. So if we don't have any other additional clauses, then the do or for directive will partition the iterations as equally as possible between the threads. Okay, so it basically simply divides the number before the loop starts running. It calculates how many iterations there are, divides that by the number of threads, and then partitions it as equally as possible, modulo any remainder if the number of threads doesn't divide the number of iterations exactly. The specification actually doesn't say exactly how it deals with the remainder, so you don't really know. So for example, if I had a loop with 7 iterations and 3 threads, it could, an implementation could either do 3 iterations and then 3 iterations and then 1 on the last thread, or it could do 3 and 2 and 2. So in principle, you don't know. Most implementations will actually do the former. We'll do 3, 3, 1, just because the modular arithmetic to calculate to deal with the remainder is slightly cheaper. Saves a few instructions. So that's absolutely fine, and it's the sensible thing to do, provided the workload on every iteration is the same. So, which is true for a lot of loops. Every iteration takes, well, at least approximately, it takes the same amount of time to execute. So it's going to require the same number of instructions. It probably requires the same number of memory references. Those memory references may not necessarily all take the same time, but at least not exactly. But that may be a good approximation. So provided our loop is well load balanced, so every iteration takes more or less the same time to execute, then giving the same number of iterations to every thread will work just fine. However, if that's not the case, then we can use the schedule clause. So that gives us a variety of options for specifying which loop iterations are executed by which thread. And so this is a clause which appears on the end of the do or for directive. So the syntax is schedule, and then a kind, and then possibly also a chunk size enclosed in braces. So the allowable kinds here are static, dynamic, guided, auto, and runtime. And I'll explain in some detail what all of those mean. And then the chunk size is just an integer expression with some positive value. Doesn't have to be a constant, can be an expression that evaluates to an integer. So it can be the chunk size can be evaluated at runtime. Doesn't have to be known at compile time. But for example, OMP do schedule dynamic, 4 is a valid option. So what have we got? Okay, let's start with static. So if we don't specify a chunk size, we use the static schedule kind, then again, as before, the iteration space is divided into approximately equal chunks, and one chunk is assigned to each thread. We are guaranteed, however, that the chunks are assigned in order. So you think of if the iterations have a logical order, the order that they would be executed sequentially. So the first chunk of iterations always goes to thread 0, and the next chunk always goes to thread 1, and so on. So there is no ambiguity there as to which chunk of iterations goes to which thread. There's just some ambiguity about how the remainder is dealt with. If we do specify a chunk size, then what happens is the iteration space is divided into chunks, each of that number of iterations, and then those chunks are assigned cyclically to each thread. Again, it's done in order. So perhaps easier to see if we do it diagrammatically. So suppose I have a loop which has 46 iterations in it, and I have 4 threads. Then if I do schedule static, then most likely what's going to happen is that, so we get 46 divided by 4 is going to be 12 if we round up. So most likely what happens is thread 0 gets the first 12 iterations, thread 1 gets the next 12, then thread 2 also gets 12, and thread 3 gets the remaining 10. If we do schedule static with a chunk size of 4, then thread 0 gets the first 4 iterations, thread 1 the next 4, thread 2 the next 4, and so on. And then we cycle round back to thread 0 again, and we just keep cycling through the thread numbers, handing out chunks of 4 iterations each until we get to the last chunk, which, if things don't divide nicely, maybe smaller than 4. Okay. Next possible option is dynamic. So dynamic schedule also divides the iteration space up into chunks of the specified chunk size. But instead of doing a cyclic assignment to threads, it assigns them on a first come, first served basis. So whenever a thread finishes a chunk, it gets assigned some other chunk in the list. And if we don't specify a chunk size, then it will default to 1. So we will do just a straight cyclic decomposition of the iteration space across the threads. Next option is guided. So this is similar to dynamic in the sense that it's also a first come, first served method. But instead of having all the chunks the same size, the chunks start off large and get exponentially smaller towards the end of the loop. So more formally, the specification says that the size of the next chunk is proportional to the number of remaining iterations, so the iterations that haven't yet been assigned to a thread, divided by the number of threads. So chunks start off big, and as the number of remaining iterations decreases, so do the chunk sizes. In this case, the chunk size parameter just specifies the minimum size of the chunk. And again, if no chunk size is specified, it defaults to 0. So the OpenMP specification doesn't actually specify the constant of proportionality here, but almost, I think, every implementation I know of uses the value 1/2. So the actual chunk size is the number of remaining iterations divided by the number of threads and then divided by 2. Okay. So for example, we have our same loop again with 46 iterations, and we specify a schedule with dynamic 3 as the kind and chunk size options. Then the first 3 iterations will go to thread 0, and then to thread 1, thread 2, thread 3. And then depending whichever thread finishes first, so in this case it's thread 1 finishes first, so it gets the next chunk in sequence. And then thread 3 finishes, so it gets the next chunk, and so on and so on. So actually, in older versions of OpenMP, you really had to, the implementation really had to start at the beginning of the loop and assign chunks in order. That restriction has now been relaxed. So in fact, it's allowable for implementations to start assigning chunks from wherever it likes. So it doesn't necessarily have to do doesn't have to necessarily start at the beginning and assign them. Threads can start anywhere they like, and then pick up chunks from other parts of the iteration space as they go along. So for guided, what happens is that the first chunk is big, okay, and then the chunks get successively smaller and smaller. But again, the first thread to finish, in this case, it was thread 2 that did this chunk. It finishes its first, so it picks up the next one in sequence, and so on and so on. And the parameter, the chunk size parameter 3 here, just says that the chunks don't get smaller than 3, except possibly for the last one if things don't divide nicely. Okay. Now, next choice is auto. So this just says, okay, this just lets the runtime, lets the OpenMP runtime have full freedom to choose its own assignment of iterations to threads. So this is basically just a mechanism for to allow implementations to do clever things if they want to, or to implement other possible loop scheduling algorithms, which are implementation specific and aren't one of the standard OpenMP ones. And then the last possible option for the schedule kind is runtime. And what this does is allows you to set the schedule using an environment variable. So you can set this environment variable called OMP_schedule, and then any loops in your code which have schedule runtime as a clause will pick up their schedule kind from that environment variable. So what use is this? Well, it means it's convenient if you want to experiment with different schedules and chunk sizes. It's a mechanism that allows you to do that without having to rebuild your code. So that's quite nice. However, if it's something that you should really only use for experimenting and tuning, and then once you've found a good value, then you should put that in the code so that you're not relying on yourself or other users to remember to set the environment variable. So it's really something that's it's really a feature that's convenient for if you're in a phase where you're doing performance tuning, and you should take it out when you sort of produce a production versions of code. So that's a lot of options. So how should you choose? Well, in the end, you probably have to do some experiments to find out which is best for a given loop. But here are some rough guidelines. So static, plain old static, or the default without specifying any schedule clause is the best if your loops are balanced, because it has the least amount of overhead associated with it. It's the cheapest thing to implement. Static with a chunk size is good for loops which have some relatively mild load imbalance. So for example, if the longest iteration takes twice as long as the average, so the imbalance isn't that big, and there is some correlation between the workload and the iteration number. Okay, so that's what I mean by smooth here, so that the workload changes fairly smoothly as either sort of increases maybe or decreases fairly smoothly as the iteration number varies. So it's good in that case, but it can itself induce some overheads. So small values may not, although you may think that static 1 is always going to be the best option to balance the load. That's not necessarily going to give you the best performance, because there's essentially, for various reasons, which I'll go into a bit more next week, small chunk sizes can induce other overheads. So it's not necessary. One is not necessarily always the optimal choice, even though that might appear to be the one that's going to balance the load best. Okay, so dynamic is most useful if your iterations have very widely varying loads. So for example, if you have some iterations that are going to take, say, 100 or 1,000 times longer to execute than other iterations, then you probably want to use dynamic, because that's going to give you the best chance of balancing the load. It also has significant overheads. So particularly if you have a small chunk size and you have a lot of cheap iterations, then you can induce a lot of overheads with dynamic. The other problem with it is that it ruins any data locality in your program. So you may end up using your caches very inefficiently because you know, if you run this, even if you run the same loop twice, then most likely you're not going to get the same assignment of iterations to threads. So you can end up with very poor cache utilization in some cases. The guided is meant to be a bit of a compromise. So it has lower overheads than dynamic, but you can run into situations where it doesn't balance the load very well. And so in particular, if you have loops where the first iterations are the most expensive, so if all the workload is biased towards the first so many iterations, then you can end up in a situation where thread 0 gets more than its fair share of the load, and the load doesn't balance very well. And finally, auto allows you to exploit some compiler-specific options if they exist. Okay, any questions about loop scheduling before I move on, or loop directives in general? Okay. So let's talk about single then. So I'm going to talk about single and then about master, and both of these are designed to deal with the case where you're inside a parallel region, but there's actually a piece of code that you want to run only on one thread and not on all the threads. So single directive indicates that a block of code is to be executed by a single thread only. So the first thread to reach the single directive will go ahead and execute the block of code. The other threads will skip over it, and there's a synchronization point at the end of the block. All the other threads will wait until the block has been executed. No surprises with the syntax. Single and end single for Fortran, enclosing a block of code. Hash pragma OMP single with a structured block after it for C and C++. So try an example that fits easily on a single slide. Suppose I have a parallel region where all threads call some function using some variable x. Okay. You then want to read a value. So you want to read variable y from a file, say, and then you want all threads to call on some other function that uses both x and y. Okay. So what you might do is say, okay, for parallel region, all threads call setup. The first thread that happens to finish setup goes ahead and calls input. In the meantime, the other threads may finish setup, in which case they skip over this block of code and wait at the end of the single directive. So there's another one of these implicit barrier synchronizations at the end of the single. Once whichever thread is doing input is finished, then that releases all the other threads and they can all carry on and execute work. Okay, so you can also have private and first private clauses on single, not used very much, and just like most of the other directives, the structured block must be such that you can't branch in or out of it. Okay, so this is a restriction on quite a lot of OpenMP directives, is that you can't jump in or out of these blocks of code. Okay. So I've already mentioned this a little bit, but this is how you do it. So by default, the end of work sharing directives, so do or for or single, have this implicit barrier synchronization point. You can remove that barrier by adding a no wait clause. However, beware, use this with care, because it's getting rid of that synchronization means that it's easy to accidentally introduce race conditions. So there may be dependencies in your code that mean that you really do need that barrier there. So for example, for the loop directives, in Fortran, the no wait goes on the end do. Okay. In C, there is no end, so it just goes on the end of it just goes at the end of the for directive. Okay, so this no wait clause suppresses the implicit barrier at the end of the loop. So that means whenever thread has finished executing its subset of loop iterations, it doesn't wait for the other threads. It just carries on executing whatever else there is in the parallel region. We have another option for essentially achieving more or less the same thing, and that's the master directive. So again, the name has now been, in the latest version of OpenMP, the name has been deprecated. It's now called masked instead of master, and it's actually been extended so that you can select arbitrary subsets of threads, but that's something that you won't find in most compiler implementations quite yet. So this indicates that the block of code should be executed by the master thread only. Okay, so it's really just equivalent to having an if statement saying, if OMP get thread num equals 0, then do something, right? So it's really just a syntactic convenience for doing that. Okay, and technically speaking, master is, for bizarre reasons which I've never quite worked out, again goes back to the sort of early design of OpenMP. Master thread is technically not a work sharing directive, and that means there is no synchronization at the end by default at the end of the block. Okay, so if you use master, then the threads other than thread 0 will skip the block and continue executing. So there's this kind of strange asymmetry or with single in this respect. And as we'll see tomorrow, there is then a way to add an explicit barrier at the end of master, and it turns out you quite often do need to do that. So it's a bit weird. It's a bit of a strange design decision. So single, it can be any thread that executes it, and there is a barrier which you can get rid of. Master, it's always thread 0 that executes it, and there isn't a barrier at the end, but you can add one explicitly if you need one. So a little bit strange. No surprises at all with the syntax, exactly what you'd expect. Okay, So if you haven't got there already, so then basically the idea here is that you can redo the Mandelbrot example the easy way, okay, and the way that you would, you would naturally do it in, normally do it in OpenMP, which is to use a work sharing do or for directive. In fact, you probably want to use one of the combined parallel region and work sharing directives for maximum compactness, if you like. And then you can experiment with different schedule clauses, because this is not the Mandelbrot example is not well load balanced. Okay, anybody have any questions? Okay, so for next, until 5 o'clock, Queven and I will still be around to answer questions. You've probably heard enough of me talking today. So what I'll do is, we'll be around if you want some help for the next 3/4 of an hour. Tomorrow I will use one of the practical session slots to talk through the solutions to the first couple of exercises. So I'll give you a chance to finish them off today if you want to, and then I'll talk through them at some point during the sessions tomorrow. If you've quite understandably had enough for today, that's absolutely fine. So we will not be in the slightest bit offended if you've had enough and you want to leave the session now. But we will be around until 5 o'clock to help anybody that wants it.